Alright, and we're back. Let's take a look at the activity series on the PowerPoint that I gave you. It's a list of the metals, and including hydrogen in this case, in order from most active at top to least active at the bottom. So lithium is the most active metal. It's among the metals, it's the most popular metal. Anything, any non-metal will leave any of the other metals to bond with lithium, leaving the other ones alone. Now this is only for single reaction replacements. So lithium is the most active. It will replace anything below it. And that's the general rule. Any metal in this list will replace anything below it, including hydrogen. So lithium will replace hydrogen in acids. Potassium will replace hydrogen in acids, all the way down to even lead. If you put lead into an acid, the lead will replace the hydrogen in the acid, making the hydrogen bubbles come up. Things below it won't. Bismuth and copper, with certain combinations of acids. If you have really super strong acids, you can get it to do that. Mercury, silver, platinum, gold. There is a way to make gold react with acids, but it's very complicated. It takes a very specific and special mixture of acids to make that happen. But silver, platinum, and gold, the three at the bottom of the list, we actually call the noble metals, because like the noble gases, they just tend not to react with anything. But hydrogen, where hydrogen is fairly important. Everything above hydrogen will replace it in an acid. Everything from sodium and above will replace hydrogen in water. So hydrogen's place in that list is only for acids. If you think, draw a line kind of where sodium is, sodium, calcium, potassium, and lithium will all replace hydrogen in water, and fairly violently. You throw lithium into water and you get these explosions and sparks and pops and all this other stuff happening. Same with potassium, calcium, and sodium. I'm not going to demo it. I don't have the stuff to demo it. I'm not going to demo it. It's just a little too dangerous for me. But that works that way. The next slide is the activity series of the halogens. And this one you're expected to have memorized because it's in order on the periodic table. Fluorine at the top, chlorine, bromine, iodine. It's pretty simple. Fluorine will replace everything below it. Chlorine, same thing. Iodine always gets left alone. Iodine is just the kid who might take a date to prom, but ends up leaving alone because he's the least popular kid there. So the examples, sodium chloride, if we have sodium chloride and we put it in an environment with fluorine gas, the fluorine will actually kick the chlorine off of the sodium and replace it, leaving chlorine gas and sodium fluoride. And this change is pretty obvious. Fluorine gas is kind of a purplish color, and chlorine gas is a greenish yellow. So if you put table salt and then you push this purple fluorine gas into it, the gas will slowly change color to be this greenish yellow, showing the chlorine being released or kicked off of this, being replaced by the fluorine. However, if you put magnesium chloride with bromine, nothing will happen. You'll get no reaction. Because chlorine is more active than bromine, meaning chlorine is more popular than bromine. So it's not going to get replaced. Magnesium will stay with chlorine instead of switching to go with bromine. Chlorine is just more active. Now if you look at the double replacement, the metathesis, two partners swapping. Now if we just put two ions in the solution and two ions in the solution into the same beaker, and they just keep floating around and they're not really doing anything, that's not really a reaction. Nothing's changing. The only three ways we get a reaction is if we have a precipitate, a solid, that's insoluble, that doesn't dissolve, it'll sink to the bottom. If we get a gas that doesn't dissolve, that bubbles out of the solution, and that's almost always hydrogen, or hydrogen sulfide. The AP test likes hydrogen sulfide, H2S, is a gas that bubbles out of solution. Or you get something like water, and that's from an acid-base reaction. We're going to focus primarily on precipitates in here. The gas one is fairly obvious in only one case. The water is only one case. So we're going to tell for precipitate forms by using solubility rules, which we talked about last year. The solubility rule song, that's on your notes. This is where I got it from. Things that are always soluble: alkali metals, group 1 metals, lithium, sodium, potassium, and ammonium, NH4+. Anytime you see those in a compound, you know for a fact it will dissolve. Nitrates and perchlorates, so NO3 and ClO4s, will always dissolve. Well, in the real world, you can make them not dissolve, but for our purposes in here, they're always going to dissolve. Chloride and iodide usually dissolve unless they're with really big cations, like lead-2 or silver or mercury-2. Those are really huge cations. They're way down at the bottom of the periodic table. Those are strong enough with the chloride and the iodide to make a solid that won't dissolve and will sink to the bottom. Sulfates, same thing. Sulfates are usually soluble unless they're with one of those big cations or a +2 from group 2 cations, so calcium, barium, or strontium. Those will make sulfates. Calcium sulfate, barium sulfate, and strontium sulfate will all make a solid and sink to the bottom. If you look at things that are usually insoluble, carbonates are almost always insoluble, unless, of course, alkali metals, group 1 metals, and ammonium. So lithium carbonate, sodium carbonate, potassium carbonate will always dissolve. Ammonium carbonate will always dissolve. Everything else is insoluble. Phosphates are usually insoluble, again, except for group 1 metals, the alkali metals, and ammonium. Hydroxides are usually insoluble, except, again, alkali metals, ammonium, and the group 2 metals, calcium, barium, strontium. Hydroxides will dissolve. Not quite as well. Calcium hydroxide doesn't dissolve quite as well as like sodium hydroxide would, but it dissolves enough, upwards of 90% in water, that we can say calcium hydroxide is soluble. Sulfides, S2-, usually insoluble, except, again, alkali metals, group 2 metals, calcium, barium, strontium, and ammonium. All of those sulfides will dissolve. All of the sulfides don't dissolve at all. So if you take a look at the solubility rules song, you know the rhythm, you know the tune, sing it in your head over and over and over again. This is the easiest way to build these connections in your brain to remember these things. Alkali metals, ammonium salts, whatever they may be, can always be depended on for solubility. And then it goes through all those things we've already done. Nitrates, always soluble. Chlorides, soluble except for the big cations. Sulfates, SO4, soluble except for the big cations and the group 2 cations, barium, strontium, calcium. Hydroxides, not soluble except for barium, strontium, calcium, and of course the alkali metals and ammonium salts. Carbonates, insoluble except for alkali metals and ammonium salts. It's all in that song. If you can get all those down, it's not quite everything that might be asked for, but if you can get all those down, you're going to have enough to really do very well on the test.